Welcome to our module on Sag values. In this video, you will learn the complexity of percentage Sag values and how to communicate when custom Sag is appropriate for a bridge design. First, let me preface this with the fact that optimal Sag values are not something that EIA is currently prepared to teach. As you will learn in the video, finding optimal Sag is currently done as an iterative geometric process. We are in the process of developing a better tool for understanding and calculating Sag. Now, let's take a step back and explain cable Sag. The term hoisting Sag is a bit misleading. This is actually what we want our cable Sag to end up as, under the weight of only the cables. I'll show that here in black. We don't end up calculating a construction Sag, but this would be an even smaller percentage. We originally hoist the cables to this construction Sag, then let them settle to the hoisting Sag. So I'll put that in as this dotted line here, of what we'd actually need to hoist the cables so that they would settle to the hoisting Sag under their dead load weight. We then predict that the dead load, decking, suspenders, etc., discussed earlier, will bring us down to the design Sag shown. I'll show here in red. And then the full dead and live load together will bring us no lower than the live load Sag, I'll show here in green. So I'll hit that live load, and the red was dead load. And these are our various Sag values. Now, we currently do not have a way of relating our various Sag values together. So what does that mean? There's no explicit equation that links the design Sag to the live load Sag to the hoisting Sag, etc. So if we decide to change, say, our design Sag, we are left with two questions. How much do we need to hoist the cables so that they settle at our desired design Sag? And then how much Sag will occur under full loading? We don't currently have the answers to these questions in the form of an equation, which is why we don't expect students to come up with custom Sag values. However, it is important to know where these values are coming from and what affects these numbers. Ultimately, the amount the cable sags will depend on how close our factor of safety for cable design is, our dead load we use, how much cable had been used, how much the cable has been used in the past, so its elastic modulus, and area of cable and cross-section. However, we can't just easily and arbitrarily increase or decrease our Sag at will because of its dependencies. For example, the regular Sag values of 4.6%, 5%, and 6.1% come from 4 1-inch cables with an exact factor of safety of 3.0. An example of this condition is done out in the Cable Sag Technical Bulletin, which is added as a textbook. However, if we only had 1 1/4-inch cables available on site, the full capacity of the cable will not be reached. So the cables would not sag to that full 6.1% of the span under live load, nor would we need hoisting to be 4.6% to sag all the way to 5% under that dead load. So if we still wanted our dead load to be at 5%, our dead load sag, we now have unknown values for what our hoisting sag would be and what our dead load plus live load sag would be. Now, calculating Sag first involves understanding the main span geometry. This is calculated in section 8.4, which is shown here, of the Bridge Builder Manual. And as you can see, when we alter Sag values, which are in here, we alter the geometry of the entire bridge, which we should now know changes the cable tension, both in the main span and the backstay. And if we want to look at the total geometric elongation of the cable, we can use the following formula. Delta L equals PL over EA, where P is cable tension, L is span, E is elastic modulus, and A is the cable area, the cross-sectional area. And as P increases from construction sag to live load sag, we can predict the geometric elongation of the cable. But in order to see how this will translate to a change in sag, we would have to split the cable into hundreds of points and calculate the elongation incrementally based on the previous point in order to arrive at the sag approximation. And to try and show this in a diagram, that would look like something starting at 1 point, or starting at 2 points, calculating that elongation there, calculating the elongation in that next bit, and that next bit, and so on and so forth for mapping out the entire cable for the bridge and seeing how much that sag increases or decreases based on its predicted percentage. Using custom sag values or more optimal sag values can and should be used for two reasons. First, if the site is geometrically constrained, it can save materials by tightening the sag values to increase freeboard instead of adding tiers. And second, using the appropriate live load sag will give more accurate numbers in our calculations. If the cables are not under a complete 6.1% sag and under live load plus dead load, this actually would create more sliding force on the abutments. So I'll make a rudimentary drawing here. Let's say our 6.1% sag, follow that line. We can, one, potentially tighten up that sag to increase our freeboard. And at the same time, we are now creating more sliding force on our abutments. Now, that concludes our lecture on sag values. And at this point, you should be aware of the complexities behind cable sag and know some basic strategies for when finding custom sag values would be important in your bridge design.